Hello. So up to now, we have learned. Uh, Actually, we have learned few things still. Uh, so, if we summarize the things what we have learned up to now under signal classification. Okay, under signal classification, we have done. Uh, we have learned three type of signal. No, two type of signal. Okay, maybe three type of signal. Okay, the first one is random and deterministic signal. T types, two types. Okay, and continuous and discrete signal, another classification. Okay, and periodic and non-periodic signal. Periodic signals. So basically, we have learned about these three type of signals. Okay, so in our course, we are mainly focused on random, sorry, not random, deterministic continuous time signal. Okay, continuous time signal. Okay, so under signal classification, we have to learn one more type, another type. Okay, that is even and odd signal. Even and odd signal. So uh, we have to discuss this future in future. Okay, but today we are not going to discuss about it. Even and odd signal. Later we will see it. What is them? So that is under signal classification, and under under the basic signals. Okay, under the basic signals, maybe we can say special signal, or normally should be referred as basic signals. And the basic signals, up to now, we have learned only one type of signal, no? Only one signal, only one basic signal, that is sinusoidal signal. Sinusoidal signal. Okay, sinusoidal signal. And we have seen that this is a periodic signal. Periodic signal. Okay. Actually, we have learned about deterministic continuous time sinusoidal signal. Okay, so we have done some few example also here. Okay, so we have learn how to find the period of this of a sinusoidal signal. And if we have a composite signal, that is the collection of sinusoidal signal, combination of sinusoidal signal. uh, uh, so in that case also, we have learned how to find the period. Okay, for a composite signal also. Okay, so actually these things we have learned up to now. Okay, and very importantly, we have another three very important basic signal. Okay, we can say basic function. Okay, so the second one is unit step function. Okay, the third one is unit impulse function. Okay, the fourth one is exponential complex exponential signal. or function. So we have to learn these three basic signals. Okay, so we will quickly see what are they. Okay, so we will see here today. We are going to learn on the basic signal about this unit step signal or unit step function and unit impulse function and complex exponential signal. Complex exponential signal. Okay, so if we go to the unit step function, unit step function. So normally unit step function is defined as ut is equal to 1 and 0, 1 when the t is greater than or equal to 0, t is when the 0 when the t is less than 0. So 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 you can do one exercise here. You can pause my video, okay, and you can try to draw this signal. Okay, you can try to draw this signal. Okay, so try to draw this signal. Take 1 or 2 minutes and try to draw this signal. Okay. Okay, so I will draw it. Okay. So it is just like this. So normally we know that we should have two variable type and the amplitude, that is ut. Okay. So you can see that when t is greater than or equal to 0, the ut is equal to 1. The t, this is the 0 axis. Okay. So t is greater than or 0. That means this side. This side. 1, 2, 3, up to infinity. Okay. So uh, this is the part where t is greater than or equal to 0. And this side is t is less than 0. So very simply you can draw the waveform, you can draw the wave, or you can draw the signal. Okay. So it is just like this. Just like this. Okay, it is a constant value. Constant value. Okay. Like this. Okay, so this is one. Okay. So this is the UT signal. Okay. So you can see that this is we can say that this is a constant DC voltage. DC voltage signal. Okay. Voltage signal that generate from a rectifier. Okay. So if you consider a rectifier, if you give a AC signal here, okay, AC signal, it will convert this AC signal into DC. Okay, and as long as this AC signal is available, let's say AC 230 watt, 230 volt. Okay, so the output DC will exist. Okay, so maybe it is 48 volt. Okay, for example, this is for example. This is an example for real-time unit step function. Okay. So anyway, basically you have to keep remember this signal. Okay. So it is very important. And also we define what is called shifted unit step function. Shifted unit step function. Okay. So this is shifted unit step function. So it is defined as ut minus t naught is equal to, in previous case, it is 1 and 0. Only two levels are there. Okay. Only two levels are there. So it is 1 and 0. Okay. So this 1 occur when t is greater than t naught. Greater than or equal to t naught. 0 occur when t is less than t naught. Okay. So this is the unit shifted unit step function definition. And if you draw the signal, it will look like this. Okay. So this is t. Okay. Now this is t naught. You can see that When t is greater than t naught, that means this side, it is 1. Okay. So it is 1 like this. Okay. When the t is less than t naught, it is 0. So here it is 0. Okay. So we have only one step. That is why we called it as a unit step function. Okay. So this value will be 1. Okay. So this is the unit step function. Okay. So what happened if this t naught is plus? Okay. So what happened if u t plus t naught? So that means if shifted to this the minus side, that means from this side t naught. Okay. So it will go like this. Okay. So this is the unit step function. Okay. So under the variable transformation, we are going to learn much about these things. But at this time, please keep remember this signal types. Okay. So I will give one example. Okay. So say that. Say that. We are given a electrical pulse. Okay, we are given electrical pulse. Okay? So that pulse is about 5 volt. Okay, and it is the pulse duration. So this time we call it pulse duration. Okay, so this is pulse duration. Pulse duration. So it is let's say it is 3 milliseconds. Okay, so this is one electrical pulse. We call this rectangle pulse. Okay, electrical rectangle pulse. We normally refer this as a rectangle pulse. Rectangle pulse. Okay. So if we draw this signal, so it will look like this. Okay. So this is a pulse. So if we draw that pulse, so this is t, and let's say it is starting from t is equal to 0, then 0 to 3 milliseconds, it is 5 volt. No? So this is a constant voltage value. Okay. So this is our signal. Okay. So now can you try to to uh, uh, write this signal in terms of unit step function? Can you try this? Okay. So the exercise is write the equation or expression. Okay, or expression for this signal for xt in terms of unit step signal and shifted unit step signal. So can you try? Okay, okay, please think. So can you write the equation for this rectangle pulse using the two unit step signal, that is unit step signal and shifted unit step signal. Okay, so try to draw it. Okay, so anyway I will explain here. So you can see that if we get 5 volt unit signal, that means 5 ut. If we multiply the ut signal by 5, so we will get this kind of signal. No? So this will be 5, and it is constant up to infinity. Okay, so t is up to infinity. So this is unit step function, 5 ut. Okay, so if you consider the shifted unit step function, okay, let's say that it is 5 u t minus 3 milliseconds. Okay, u, this is u, t minus 3 millisecond. So you know that t minus 3 millisecond means it is starting from here and it is constant value is here. Okay, so it is normally 1. So if it is multiplied by 5, this also will be 5. So what happen if we subtract this shifted unit impulse, this shifted unit impulse from this impulse? What happened? What we left? So you can see that this value and this value. Okay, so this is 3 millimeter. Okay, so this is 3 millisecond. So from 0 to 3 millisecond, it is 5 minus 0. Okay, from 0 to 3 millisecond, it is 5 minus 0. 5 minus 0, that is 5 volt. Okay, what happened 3 millisecond to infinity? That is 5 minus 5. That is 5 minus 5, that you will get 0. So if you subtract u t minus 3 by ut, that is ut minus ut minus 3, okay, you will get only this part up to 3 milliseconds. Okay, so this is 1 basically. If you multiply this by 5, that means if we weighted it with 5, you will get 5t. Okay, so you can see that we can we can express that xt in terms of 2 unit step function, ut minus ut minus 3. So in general, this is very important derivation, because almost every signal we can express using approximately using unit step function. For example, if we have this kind of signal, say this is the signal txt, okay, so you have to model this signal. Okay, so you can approximate signal by with the small step like this. Okay, with the small step you can uh, approximate this signal like this. So now this is a unit steps are there. So steps are there. So each step can be expressed using a unit step function, no? Using a unit step function. So you can see that this kind of continuous signal you can denote, or you can express in terms of unit step signal. Okay. That is one very important thing you should keep remember. Okay. So we will do some example later. Okay. Uh, so we are going to the third signal, that is unit impulse signal. Okay, unit impulse signal. Okay, this is our third signal. First one is sinusoidal, second one is unit step, and this is our unit impulse signal. Okay, so what is unit impulse signal? So I will I'm not going to explain it much more because it will confuse you, but when we are doing Fourier transform and Fourier series, we will further study this. Okay, at this time please try to remember. Okay, so it is just like this. Okay, so normally unit impulse signal is uh, denoted as delta t. Okay, delta t. The unit step signal ut, okay, this is unit step signal ut denoted by ut, but unit impulse signal is denoted by delta t. Okay, so the unit impulse signal delta t, it is something like this. Okay, so it is just an impulse. So this is called impulse. Okay, so this time is actually 0. Very small time duration is there. So that is why we call it impulse. Okay, so this is a pulse. If you have a time it is a pulse. Okay, this is a pulse. Okay, so if you reduce this pulse duration and 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 if the pulse duration is 0, we normally refer to as impulse. So it is an impulse. So there is no time duration here. It is almost 0. Delta t is 0, is very near to 0. Okay, so that is the impulse. Okay, so this is look like a discrete one. Okay, but actually this is not discrete one. Keep remember that this is a continuous type. This is a continuous impulse signal, unit impulse signal, continuous time unit impulse signal. Okay, unit impulse signal. Discrete version is also there, but we are not going to learn about the discrete version. We will only focus on the continuous focus, continuous format. Okay, so it is continuous time unit impulse signal. Okay, so it is draw like this, and it is denoted like this one. Okay, so there are some definition actually. This is very special function. Okay, it is not an ordinary function actually. Okay, so in real life we can't achieve this kind of impulse. Okay, because the time duration is 0, so that kind of pulse practically we can't achieve in real life. We can't achieve. Okay, so this is completely a theoretical mathematical mathematical approach. Okay, mathematical definition. Okay, so normally it is defined as, okay, so there are actually we can say that there are basically two definitions. One is very small, within very small duration. So this is plus sigma to minus sigma. So this is very small duration. Okay, so if we integrate it with the duration small, that delta t dt, you will get 1. So what is this actually? This area, no? The area of the impulse, area of the impulse. So you know that if we integrate it from here to here, you will get this area. That is the definition of integral. Okay, you will get this area, and you can see that that area is equal to 1. Okay, so if sometime it is normally here 1 is here, so that means the area is 1. Okay, so that means the area is 1. Okay, so that is one thing to remember. This is one definition, and the other definition is, another definition is, if we have another function, okay, so that function may be from minus infinity to plus infinity. Whatever the limit that function have, this minus to plus means the limit of this 5t, okay, into dt, delta t. So if any function is multiplied by a delta t and it is integrated within this pulse, within this signal limits, you will get 5 0. Okay, so you will get 5 0. This is one another definition. Okay, so we are using this definition many times in future when we are doing Fourier transform and Fourier series. Okay, so at this time please keep remember these properties. Okay, these are actually definition, and another definition is there, that is shifted version. So it is like this: minus infinity to plus infinity, 5 t delta t minus t naught is equal to 5 t naught. Okay, so what is this delta t minus t naught? So it is shifted impulse. So it is like this: t naught when the delta t is here, okay, at 0, but delta t minus t naught is, it is shifted to here. What if delta t plus t naught, it will be shifted to here, this side. Okay, This is delta t plus t naught. Okay, so this is delta t minus t naught. Please remember this, and we will learn more about this in variable transformation. Okay, we are going to learn, but this time you can just keep this in reminder. Okay, you don't know how to happen this. Okay, but when we are learning the time transformation, you can understand what is ongoing here. Okay, but at this time no need. Okay. Okay, so these are the most important definition actually. Okay, these are definition of the impulse signal, and we have two property also. Okay, one property is we call time reversal property. Time reversal property. Okay, so these properties are also you can learn in the time transformation. Okay, what is this time reversal? And also the second property we called time scaling. These things you can learn. Okay, so in time reversal, that property stated that delta minus t is equal to delta t. Okay, so that is delta minus t is equal to delta t. Okay, and time scaling denote that delta at, this kind of signal is equal to 1 by absolute value of a delta t. So these are the two properties, time reversal and time scale. Okay, so if you want to find more details about this unit step signal and unit impulse signal, you can refer our textbook. Okay, so here so under the in first chapter, under basic continuous time signal, you can find these basic signals. Okay, so first one is a unit step signal. So we have learned this unit step signal and the shifted unit step signal. Okay, so it is look like this. These are the definition, this one and this one. Okay, so you have to keep remember this. And the unit impulse function. Okay, so it is like this. Actually here it is not denoted, but it is just denoting, put in arrow here. Okay, by uh, by uh, by writing arrow here, drawing arrow here. Okay, so 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 we have discussed this definition. Okay, and we have seen this definition, and also we have seen this definition. Okay, so these are the three basic definition. Sometime we have to use this one. Okay, and this one and this one. Okay, these three, 1 2 3. And properties are this is, you see that unit steps in signal, and this is shifted unit step signal delta t minus t naught. Okay, so here you can see the two properties. Okay, so this is our first property, time scaling. Okay, and this is our second property, time shifting. So basically you have to remember this signal graph. Okay, and you have to remember these properties, this one, and this one, these three properties, and these three definition, this one, and this one, those three definitions, and also this two property, 1 2. Okay, so that is unit impulse function. Okay, so now we have to learn another important function, that is complex exponential function. That is complex exponential function or signal. Okay. So what is complex exponential function? So before that we have two exponential function, that is real exponential function. Real exponential function. Okay. Acha. So normally it is referred as e to the power alpha t. Okay. So this alpha is a real value. Real value. Okay. Real value. So you will get uh, uh, this kind of signal here. This kind of signal. It is we said that it is exponentially increasing. Okay. So this signal is exponentially increasing. So this is the real exponential signal. Okay, I will draw it here. Okay, and that is the real exponential signal. So it is like this. So anyone can tell what is this point? This is t and this is our e alpha t, no? Okay. So this is actually when the alpha is plus, it is exponentially increasing. When the alpha is plus, okay, when alpha is plus value, plus real value, okay, alpha is plus real value, it should be a real value, it is increasing, exponentially increasing. Okay, so it is like that. So what is this point, this crossing point, 0% point? That is actually so this is not 0% point. Okay. 0% point normally we referred as the excess is crossing point. Okay, so this is the y-axis crossing point. Okay, at x is 0 or t is 0. So what is this value? When the t is 0, e to the power 0. So e to the power 0, you know that it is 1. Okay. So you know that this e, this is we called Euler number, no? Euler number. So this has a value actually. I can't remember. You can find the internet. Okay. Okay. So this is the exponential signal when the alpha is a plus value. When the alpha is a minus value, it is discretion. So when the alpha is a minus value, that means if t minus alpha t, so it is like this, exponentially decreasing. And in same manner, you can see that this is the this value is 1. So these are real exponential signal. The exponentially increasing signal, exponentially increasing signal, and exponentially decreasing signal. Okay. So I think if you have learned about capacitor charging and discharging, you may remember that capacitor charging, discharging is like this. Discharging is like this. Okay. Actually, this is the exponential signal. Okay. So it is this voltage with respect to time. If you discharge the capacitor, charge capacitor using a load, so the charge in the voltage will be reducing like this, exponential. So as I can remember, it is Vs e to the power minus t by tau. No, you can I can't remember the exact equation. This tau is the time constant RC. Okay, so this is supply voltage. Okay, so if you're interested, you can see. Anyway, this is a real-time example for exponentially decaying signal, exponentially decreasing signal. Okay. So you can, as I can remember, the charging also, charging is like this. Okay. So this is also can be represented using exponential signal as 1 minus e to the power minus t by tau. Multiplied by Vs. Okay, so this is the capacitor. This is charging. When you connect a battery through a capacitor, the capacitor is charging. So this is the charging curve. The voltage, how the voltage is increasing. Okay, so it is like this, as I can remember. Please, please see this equation are correct. Okay, I'm not sure. Okay, so anyway, you have to keep this pattern. Okay, keep this what we call the keep. You have to keep remembering this shape. Okay. So that is complex real exponential signal. The complex exponential signal is actually this is the important signal. Complex exponential signal. Exponential signal. Okay. So we normally refer it as e to the power j omega naught. Okay. So it is e to the power j omega naught t. Okay. If it is t, okay, as I can remember, let's see. Yeah, it is the uh, increasing sinusoidal signal. Okay. So when e to the power j omega naught t, so this j is the complex number, no? Complex value. This j is a root minus root 1 minus 1 root minus 1, this j. Okay. So this is a complex value j omega naught t. So this is increasing signal like this. Okay, like this. It is the amplitude is increasing. So this is a sinusoidal signal actually, but the amplitude is increasing. So we normally refer this as increasing, exponentially increasing sinusoidal wave. Okay. And what if this is minus? It will be decreasing. Okay. It will be decreasing. So what happens if it is minus? So it will be like this. So this is t, this is e to the power minus j omega naught t. Okay. So this is exponentially uh, decreasing sinusoidal signal. Sinusoidal signal. So very important property of this signal is this is a periodic signal. Okay. So I am wondering how this is periodic, because you can see that if you if you see, this point will not repeat, no? You can see that this point is not repeating again. Okay, you will get a different value here, different value. Okay, so this is not repeating physically, but mathematically, we can prove that this is a periodic signal and period is 2 pi by omega naught. So how can you prove this? I think you can try it. Now you have knowledge to do that prove. Okay. So I hope you can prove, if you can prove this. Okay. To prove this, you have to use the Euler formula. So what is the Euler formula? You already know that j omega naught t. At the beginning of the course, I have mentioned you that we are going to use this Euler formula very often throughout this course. Okay. So e to the power j omega naught t, we know that cos omega naught t plus j sine omega naught t. Okay. So if we write e to the power minus j omega naught t, it will be cos omega naught t plus, sorry, minus, here it is minus, when this minus, here also minus j sine omega naught t. So this is the Euler formula. So you can see that this is a two composite signal. No? This is a composite signal which has two sinusoidal signal. So if you consider this sinusoidal signal, what is the period here? That is 2 pi by omega naught. If you consider this sinusoidal signal, that period also 2 pi by omega naught. So for the total signal, the period will be 2 pi by omega naught. Okay. And in this case, it is also same. This period is 2 pi by omega naught. We already have 2. This period is 2 pi by omega naught. We already have 2. Then t is 2 pi by omega naught. Okay. So these are the basic thing we have to learn about the other basic signal. Okay, so I will again summarize the things that we have learned. Okay, I will use our uh, textbook, primary textbook, because the graphs are clear here. When I draw the graph, it is not clear. Okay, so you can see that this is a unit step function. So we are today we have learned another three new basic function, that is unit step function, unit impulse function, complex exponential function. Those three we have learned. Please keep remember. So this is the unit step function. It is defining like this. Only one step is there. This is 0 and this is 1. One step. That is why we call it unit step. Okay. So you can see that. So when the t is in 0, the in plus direction, it has a value, constant value 1. So this is the unit shifted unit function. Okay. So you have learned that using the unit step function and shifted unit step function, you can approximate any signal. Okay, so that is the things you have to understand. The another thing is unit impulse function. So this is mathematical function. Actually, this is not a real world function. Okay, so basically you have to keep remember these three definition: this one, and this one. And also you have to keep remember these properties, this one, and this is the unit step function. It is just an impulse. Okay, and this is a shifted impulse. Okay, so these things you have to keep remember, you have to understand. Okay, the other thing is a complex exponential signal. So this is the E j omega naught t. Okay, so this j represent the complex value. Okay, so this is a complex exponential signal. So you can see that this is a sinusoidally increasing. When this omega naught is plus, okay, here it is plus, this is increasing. Okay, and if it is minus j omega naught t, or this omega naught is 0, omega naught is minus, so it will be a decaying exponential sinusoidal signal, sinusoidally decaying signal. Okay, so you can see that the Euler formula is there. Okay, so using the Euler formula, we can prove that this is a periodic signal, but we can't see it physically. This is a periodic, but anyway, it is a periodic signal. Mathematically, it is a periodic signal. So the period is this. Okay. So, and also we have learned additionally the real exponential signal. So this is the increasing exponential signal, exponentially increasing signal. Okay, so this is exponentially decreasing signal. So the capacitor charging and discharging are related with this exponential, real exponential signals. Okay, so that are the things we have learned. Okay, so we will do some example using this concept. Okay, so then you can get more clear idea. Okay, thank you.